Hello everyone, my name is Sunowi Birama from Department of Electrical and Information Engineering, Faculty of Engineering, Universitas Gadjah Mada, Indonesia. In this special occasion, I would like to present our research entitled A Survey of Event Detection Methods for Eye Movements Classification in Smooth Pursuit-Based Interactive Applications. Currently, we are developing interactive applications in our laboratory. One important question that we are trying to solve is how to interact with an interactive applications. We may know that in a traditional way, we can interact with interactive applications by using mouse and keyboards or touchscreen to send information to the computer and to obtain various information by tapping the screen. However, in the pandemic era, some people may choose interactive applications with a voice-over or voice recognition system, or by using their gaze to control the interactive application without touching the screen. And in this study, we try to focus our study in the gaze-based interactive applications because this gaze-based interactive application gives benefit to motion-impaired people, and then it provides faster interaction as well as more intuitive for the user to communicate with the computer. In the case-based interactive application, there are several components such as application contents that provides information to the users, and then the user itself that control the applications, the user's object of interest such as the button that triggers the application content, and the eye tracker that is installed beneath the monitor. There are at least three most popular types of eye movements, which are fixations, saccades, and smooth pursuits. Please look at button number 1 in your screen for a while. And if you are looking at the button number 1 for a while, for about 200 until 300 milliseconds, you perform a fixational eye movements. Please kindly take a look at the button number 1 again, and then please look at the button number 2. And if you perform a gazing from button number 1 to button number 2, you perform a saccadic eye movement, which is rapid eye movements from an object to another object. And please try to look at the button number 3. While it's moving, please try to trace the trajectory of button number 3. As you may see, when you look at the button number 3, try to trace the button number 3 from the prior position to its new position. You perform a smooth pursuit eye movements, which is a slower eye movements while pursuing an object. This is an example of smooth pursuit application, which is by using our smooth pursuit eye movements, we can control the application in the computer without even calibrating our eyes or our gaze position to a certain object of interest at screen. So when you trace the button or following the button, then you elicit the smooth pursuit eye movement. And then by choosing specific button, you can trigger specific content in the interactive applications. There are at least 3 main challenges when we develop a gaze-based interactive application, according to Koh et al. In 2010. The first challenge is data processing. As we may know that when we get the data from the eye tracking sensors, the data is inevitably full of noise because we cannot control whether there are certain information that we don't want to be included in our program. And then the second challenge is the classification of eye movement types. So when we record the eye movements from an eye tracking sensor, the three types of eye movements are mixed together. And then the third challenge when we develop the case-based interactive applications is how to map a certain token of eye movements to a certain action that trigger the computer. In our research, we would like to isolate the smooth pursuit from other types of eye movements. Therefore, we will focus our discussion in how to classify various eye movement types. If we talk about event detection in the eye tracking research, we know that event detection equals to types of eye movement itself. So this study focused on event detection methods that consider smooth pursuit eye movements in the results of event detection algorithms. And there are actually two main algorithms that are currently used to detect eye movements or to detect event. The first method is a threshold-based method, and then the second method is probability-based method. In the threshold-based method, we can detect event of eye movements by implementing a certain threshold value so that when we measure up an eye movements with a certain threshold, we can classify the eye movements by looking at the threshold itself. For example, in this slide, we can see that the eye movement with type A is larger than a certain threshold, and then the eye movement with type B is smaller with a certain threshold value. For example, there is an algorithm called IVVT, or velocity and velocity threshold identifications. In this algorithm, we can measure point-to-point velocity from the case point number 1 to the case point number 2, and then from the case point number 2 to a case point number 3. So there are two velocity values. We can then compare this velocity value. If the value is larger than a saccade velocity threshold, then we can classify this segment as a saccadic eye movements or saccade eye movements. And then if the velocity is lower than saccade velocity threshold, however larger than smooth pursuit velocity threshold, then we can classify this segment as smooth pursuit eye movements. Otherwise, this is a fixational eye movements. This algorithm is actually very simple to be implemented. However, this usually depends on a clear and visible differences between eye movements. The second method is called a probability-based event detection method. For example, in this case, there is IBDT, or Bayesian decision theory identifications. Suppose there are three events called fixations, smooth pursuit, and saccades. IBDT defines prior probability of each event, and then after that, given a segment of case points, IBDT defines the likelihood. And then after that, using the Bayes theorem, IBDT calculates the posterior probability of each event. Even with the highest posterior probability is claimed as the type of eye movements of the evaluated segment. The third one is combination between threshold and probability-based event detection method. For example, attention focus Kalman filter. This algorithm tries to calculate the difference between the predicted and the observed eye velocity, and then after that, the difference of the velocity subsequently compared with the threshold value. So the difference of the velocity is compared, for example, with the saccade threshold. If it's larger, then it's classified as saccade, and if it's lower or larger than smooth pursuit, and then it can be classified as smooth pursuit eye movements. In our paper, we present a general comparison of event detection methods. You can see in the table 1, there are several algorithms and their properties, such as whether this algorithm includes signal denoising, include adjusted parameter values, and how this algorithm is implemented in real-time implementations. In the environment with high level of noise, perhaps we need to consider how this algorithm denoise or remove the noise that is resulted from real-world implementations. In our case, when we look at the table, most of the evaluated methods have included the denoising algorithm. However, perhaps we may try to ask ourselves how to choose a suitable denoising methods. The answer is by considering the characteristic of the eye movements. A paper by Pekanen considered the eye movement or a case of humans like a linear trajectory. So they propose event detection method by considering that eye movement signal can be modeled into several independent linear functions. In the parameter values adjustment, we can see that the classification module should provide an easy way to be implemented in real-time protocol. It is preferable, however, that our algorithm is easy to be adjusted. So in this case, general parameter values may provide more flexibility to be implemented in real-time protocol. However, the drawbacks may be that the compatibility issue with different group of people. Additionally, when we implement automatic updated values, perhaps we have to pay the higher computational costs. So there are several algorithms that can be implemented in real time or several algorithms that cannot be implemented in real time. For example, some papers by Larson et al., they propose algorithms that cannot be implemented in real-time system. So we have to ask ourselves what type of research that we want to implement, whether we implement our algorithm in real-time system or whether we implement in offline system. This question should be asked before we choose the event detection algorithms. And perhaps we may ask ourselves which event detection method is the best. Currently, there has been no direct comparisons because most of the methods run in different datasets. It is still difficult to state which event detection is the best in terms of their relative performance. And in future, we really hope that there is a direct comparison between event detection methods. When we talk about implementation of event detection methods, we may see that event detection can be implemented in the case-based interactive applications because by using this event detection, we can map certain tokens of eye movements to control content of interactive applications. We also see that event detection methods can be implemented in safety driving, such as a paper by Kasnesi et al. In 2015. They tried to detect certain oculomotor events that may be used as a signal to detect a potential traffic hazard that might be overlooked by the driver. In conclusion, in developing smooth pursuit-based applications, eye movement classification is very important to be addressed. And in this paper, we present a general comparison of existing event detection method that has been surveyed by considering smooth pursuit eye movements. And in future, we wish our review paper may be used as a baseline to implement event detection methods in experimental settings to compare their real performance.